So today is our last lesson on the exponential functions. This is the doing optimization problems. You can see that that next lesson is going to be about trigonometric functions, which is kind of the other half of this unit. So today we're just looking at the optimization problems using exponentials. I think it's a really important section. A lot of the questions, of course, you can predict an application or thinking could come from this area. So I'm going to go through the three that are on here, and then I'm going to do the first one from your assignment, just because I think it will help you just see how you can use these things in a context. So let's go through the first one. It says the effectiveness of studying for an exam depends on how many hours you study. Some experiments show that if the effectiveness E is put on a scale from 1 to 10, then E of t is equal to this expression, where t is the number of hours spent studying. If a student has up to 30 hours, how many hours are needed for maximum effectiveness? So, again, let's just look at what this might look like before we begin. So E of t, so E of x is equal to 0.5 bracket 10 plus x times E. Just going to put exp, so make sure GeoGebra knows what I mean, and then negative x over 20. Okay, and that's the formula. Just double check it here. 0.5 bracket 10 plus x e to the power of negative x over 20. Okay, and you can see that it rises, reaches a kind of peak, and then starts to fall as you're losing sleep, or you're doing too much cramming, or whatever it is. So we can just use GeoGebra to get the maximum. Here we go. What's the maximum of E between 0 and 30 hours? Oh, sorry, between 0 and 30 hours. Okay, and you can see we're looking for an answer like 20, and the effectiveness is like 87 or 8.7 out of 10. Okay, so let's go back now and see how would we actually look at this question in optimization. So if you recall from optimization, what we needed to do is find an expression, find its max, and make sure it was in one variable. Now, here you already have this is already in one variable. So there really isn't any setup to be done here particularly. What we need to do is we need to follow a three-step process. 1, take the derivative of E of t. 2, find the critical points. 3, prove it's the absolute max. Okay, so that's all we need to do. And then let's just go through and find this right now. So the derivative of this one, okay, we have 0.5 times 10 plus t e to the power of negative t over 20, like that. Okay, now you can, I think it's probably a good idea here to distribute that 0.5. So let's say we distributed the 0.5. So we could say E of t is equal to 5 plus 0.5 t e to the negative t over 20. And this, I think, is an easier question to kind of deal with. Of course, you could do the first one. You could basically pretend there's a little, you could pretend there's a little 1 up there, and then you could bring the 1 down. All of this becomes a 0, and then you take the derivative of the inside. That would work, but I think it's easier to distribute here. So let's distribute. The derivative, of course, is going to be equal to 0 plus, okay, so again, this is a product rule, right? So we have 0.5t is our first function, and then it's multiplied by e to the negative t over 20. So what we're going to need to do here is do a quick product rule. So let's say g of x is, or g of t, sorry, is 0.5t. h of t is e to the power of negative t over 20. And therefore, g prime is equal to 0.5, and h prime is equal to, okay, so we know with an exponential, we copy it out again, we multiply by the correction factor. Of course, you don't really need to do the correction factor in this one because it's base e, and then you multiply by the derivative of the exponent. So to make that a little simpler, we can just say negative e to the power of negative t over 20 all over 20. Okay, so something like that would be the derivative of h prime, although, you know, it might just be easier to just say the 1 over 20 and then just leave the 1 over 20 separate so we have an easier time factoring it later. I think probably true. So let's leave it like that. I think that's probably fine. Okay, now the derivative e prime at t. Okay, so we need let's write, we need g of t times h prime plus h of t times g prime, and e prime t is therefore equal to, okay, we start with g of t, 0.5t, then we do h prime, negative 1 over 20 e to the power of negative t over 20. Oops. Okay, then we're going to add h, which is e to the power of negative t over 20, and then times g prime, which is simply 0.5. Okay, now what we can do is we can do some common factoring. So I noticed both of these things have a 0.5, and both of these things have an e to the power of negative t over 20. And then if I look at what's left, I see I have negative t over 20, right? All right, let's just keep them separate. So I have a t, I have a negative 1 over 20 on the left side. On the right side, I have nothing, right? I just have a positive 1 because the 0.5 came to the front and the e came to the front, right? So again, just to make this a little bit simpler, hopefully to see, if we color in the common factors, right? They both had that red factor, which is why I brought that to the front. They both had this factor of 0.5. So that one had a 0.5 and that one had a 0.5, and that is why that one was brought to the front. And then if you just look at whatever I didn't color in, right? A t, a negative 1 over 20, and then everything was gone from here, so only a 1 is left, right? So you come to this conclusion, e prime at t is equal to 0.5 e to the negative t over 20, and then we're going to multiply that by 1 minus t over 20, right? So that's what you have. Now when you are solving these things, e prime t equals 0, you know how to solve a factored equation. You look at each factor and ask, could this ever be 0? So let's analyze. 0.5 is never equal to 0. E to the power of negative t over 20 is never equal to 0 because it's an exponential function. Exponential functions are never equal to 0 unless they're shifted. And that leaves us with 1 minus t over 20, which you can see is equal to 0 when 20 minus t is equal to 0, which is when t is actually 20. So our critical point here, t is equal to 20. Okay? So look at what we've done. We found the derivative. Okay? We found the critical point. There was only one. And now we have to prove it's the absolute max. Now when you're proving the absolute max, so to prove the absolute max, you have two choices. Number one, if there is only one critical point, show that it is a max. Again, what can you do here? You can do the first derivative test, or you can do the second derivative test, whichever. Number two, if the domain is closed, check all critical points and all endpoints. Up to you which one of these two things you do, but you need to do one or the other. For us, let's do the second one. So let's compare e of 0. Remember the domain. So remember just the domain here comes from the question. The student has 30 hours to study, it said, right? So we could have 0. Obviously, you can't study less than 0 hours. Less than t is less than 30. So what we should do is we should check the effectiveness of studying at 0 versus the effectiveness of studying 20 versus the effectiveness of studying 30, right? Now again, I'm not going to go through and sub all these things in. Let's just go back to our function and sub them in. E of 0 is 5. That one I should have known because that one's easy. I should have known e of 0 is 5, right? Because if you go back up to the e function, particularly this one, e to the power of 0 is a 1. Oh yeah, sorry. So sorry, the t here is 0, so everything else in this chunk would be 0, and then you're just left with the 5, right? So that makes sense. So e of 0 is 5, okay? E of 20, if we're plugging in 20, we get an answer of 8.68. And then finally, e of 30, which would be 8.35. So since E20 is the highest among the candidates, E20 is absolute max. Now let's just go back and read what it said. If a student has up to 30 hours for studying, how many hours are needed for maximum effectiveness? So we say, therefore, 20 hours are needed for maximum effectiveness. Okay? And that's how you would answer that one. So again, really good question. It combines a lot of what we learned last unit and what we learned in this unit. The setup is often a little bit easier, but of course the derivative, you need to use your new skills, and you still need to make sure you prove it is the absolute max. We have a lot of people that always forget to do that, so make sure that you do that. Okay, let's try number 2. So it says a rumor spreads through the population in such a way that after t hours after it started, the percent of people having involved in passing it on is given by this equation. What is the highest percent of people involved in spreading the rumor within the first 3 hours? When does this occur? Okay, so again, number 1, let's change what I wrote above a little bit. Look for a domain. Number 2, look for a derivative. Number 3, maximize it or optimize it, or set the derivative to 0, and then prove it's an absolute max. Okay? We'll see what I wrote up top. Yeah, okay, so that's fine. Alright, so number 1, a domain here. The domain, it says within the first 3 hours. So 0 is less than equal to t is less than equal to 3 would be your domain. Okay, so we know, again, in a closed domain question, your proof is going to be pretty easy. You just plug in 0, plug in 3, and then compare those with the other question. Now, the function here is p of t is 100 e to the negative t minus e to the negative 4t. Okay, so let's do the derivative. Again, you're free if you like to distribute in this question. If that makes it easier for you, then go ahead and do it. I'm going to do it the other way this time. So we're going to do p of t is equal to 100 and then times this bracket Okay, so the 100 is just a constant. So sorry. So if I take the dy, sorry, let me write this properly. dp of dt, right? How does p change as t changes? You can just bring that 100 to the front and then take the derivative of the inside part. You don't need to worry about the you don't need to worry about that 100. You can distribute it, or you can do what I'm doing here. Okay, so what I'm going to do here is I'm going to take the derivative, so p prime t. Sorry, not sure why this went up in the exponent here. Okay, so p prime t, we get 100, and then we're going to take the derivative. So the derivative here is negative, so we get e to the negative t, right? Copy it out exactly as you saw it. And then times its derivative, which is a negative 1. Then you have e to the, negative 4t. I think that's a typo there. Okay, and so then you copy it out like you see it, and then you multiply by its derivative, which is a negative 4. So p prime of t is equal to 100. Okay, now we're going to have the negative e and the negative 4 make a positive, so we have 4e to the negative 4t, and then we have minus e to the negative t. Okay, now a mistake that is going to get made, and I hope you are not the one to make it, is what to do with this. Okay, so understand you cannot solve that thing when that thing is equal to 0 without factoring. So factor it. Okay, now this becomes a bit tricky because what happens, like what is the common factor between these two things, right? Here's what I'm going to suggest. Let's factor out e to the power of negative t. Now, in order to do this, what I suggest you do, and if you can do it in your head, obviously do it in your head, but if you're not sure, when you factor something, right? Let's just go back, let's just factor something really simple just to remind us how this works for a sec. So let's say you're factoring x cubed minus x squared. Okay, what would you do there? You would take an x squared to the front, and then you would take each part, and you would divide each part by x squared, right? Now you're probably so good at this, you just do it in your head, but you would end up with that, right? But to remember what you're actually doing, you're pulling something to the front, and then you're dividing every term by it. So I'm going to pull an e to the negative t to the front, and then I'm going to divide every term by that amount. Okay? Okay? And then obviously the second part is just minus 1 because it's e to the minus t over itself. Now, what do you do when you have two powers, right, with the same base? You can subtract the exponents, right? Okay, so look what happens in this bracket when you expand it. So the 4 is still there. Now I have e to the power of negative 4t minus negative t, all as one thing, and then minus 1. So what actually happens in that bracket, if we just skip the step there, e to the negative t, okay, we have 4e. Now, negative 4t subtract negative t becomes negative 3t, right? Because you're basically subtracting a negative, you add 1, and now this is what we have. Now remember, we want to know when p prime t is equal to 0. So our candidates are when 100 is equal to 0, but of course 100 is never 0. E to the negative t is also never 0, so that can't be an answer. So our only choice here is when 4e to the negative 3t minus 1 is equal to 0. Now, this would be true when 4e to the negative 3t is equal to 1, which in turn would be true when e to the power of negative 3t would be equal to 1/4, right? And so, how do I get that 3t down out of the exponent? I'm going to do the natural logarithm of both sides. Okay? What happens when I do that? On the left side, the 3t comes down to the front, right? Because it's an exponent that can move down to the front of the... And on the other side, I get a number, right? So what is that? What is that number? What's ln of 1/4? Okay, so I get, let's just round it to 5 for now, negative 1,38629. Okay, so now what I'm going to do, of course I know that 3t ln e is just equal to 1, which means t is equal to negative 1.386229 divided by 3. Okay, now something's wrong because, oh, I see. Sorry, my exponent up here was negative. So why do I know something's wrong is because this answer is outside the domain. So it's not impossible that you're going to get a question where it's outside the domain, but it probably isn't very likely because you could solve it without knowing any calculus. You would just check the endpoints. So I'm probably not going to give that to you. Sorry, I made a mistake here where from this step to this step, I forgot the negative. So let's bring the negative there, and then it would also be going there. And just to make this a bit clearer, we'll go like that. So we get t is equal to let's take that number a and divide it by 3. Divide it by -3. And we get 0.4621. This seems like a reasonable answer. So, it's like 0.5 hours into the process. What is the highest percent of people involved in spreading the rumor within the first 3 hours? When does this occur? Well, I'm pretty sure it occurs at 0.4621, but I'm not totally sure because I have to check the other options, right? So I have a critical point. T is equal to 0.4621. Okay. Now, I want to prove now that it's the absolute max. So to prove, show that it is, again, I have two choices. I can show that it is the only critical point and also a max, or check what was our function called? P of 0, P of 0.4621, and P of 3. It has to be one of those three numbers, right? We know. Again, it's up to you, right? The second derivative probably wouldn't be too hard to do here. You just go back to, you'd go back to this step and take the derivative again and then sub in. I don't know. I mean, you could also do the first derivative test. You could sub in a number into your first derivative, but to me, the easier thing to do is we'll just plug in these three values into the equation. So let's go and look at the original equation again. So 100, so we have 100 e to the negative x minus e to the negative 4x. Okay, you can see this is a really interesting looking function. It starts at 0, it really rapidly rises, and then it has a turning point, and then it sort of softens out into a horizontal asymptote over time. So our candidates, right? We have 0 and f of 0. Well, that's certainly not going to work because e to the 0 and e to the 0 are both 1. So you have 1 take away 1 in the bracket, and you get nothing. Then we have 3 and f of 3. And that, after 3 hours, only 5% of the people are involved in spreading the rumor. So we have point B and f of B, which is the max, right? So, again, let's just type this out. We'll just grab it. Okay, so what we're doing here is we're just demonstrating the three candidates. So since P of 0.4621 is greater than P of 3, which is greater than P of 0, the absolute max is 47.24% of the people involved. And this occurred 0.4621 hours after the rumor started. So again, I don't think if it says change to minutes, by the way, which I did ask on the last test, to change it to minutes, you're just going to go 0.4621 times 60, and we'll just 27.7 minutes, right? So I don't think you're going to need to do that, but if you did need to do it, then there you go. All right. That's that done. Now, one more. It says a certain radioactive material decays exponentially. The percent of material left after t years is given by this equation. Now, interestingly, now that you know some more about exponentials, the half-life actually doesn't need to be given the way that it used to be, right? Where the base was always 1/2. In fact, in calculus, it's better to use a base of e when you're doing half-life, but anyway, we can look at that if any of you have a question. So it says determine the half-life of the substance. So the half-life of the substance, right? So A would be the amount of time it takes for P of 0, right, to decay to p of 0 over 2, right? So like, how much did you start with, and how long does it take to get to half of that? So in our question, p of 0 is equal to 100 times 1.2 to the power of 0, which is equal to 100. The number that we are looking for here then, p of t, is equal to 50. We want to know what t, right, how much time happens by the time it shrinks to half of its original amount. So what we're going to do, we're going to set our equation equal to 50. 100, 1.2 to the power of negative t. Okay, and then we're just going to solve it. So we actually don't need any calculus to do this, but we'll just to show. The 100 goes over to the other side. You get 1/2 equals 1.2 to the negative t, right? Then what you do, you take the natural logarithm of both sides. Again, you could take the regular log of both sides if you want, but sorry, that isn't quite clear. It should be inside the bracket. Okay, then what we can do is we go bring the negative t to the front, like so, and then we get the answer. And all we got to do there is just bring the negative to the other side, and we'll get the amount of time that it takes. Okay, so let's go ahead and do that. So let's draw it first. So we'll go 100, 1.2 to the power of negative x. So this is the decay curve we're looking at. Okay, and we said that the half-life occurs, so let's call it h. H occurs at, actually let's do a little h, occurs at the negative of ln 0.5 divided by ln 1.2. And so what I'm getting there is the number 3.8018. Now, if I were to graph that point, right, you notice that the curve, it has decayed from 100 down to 50. And if I were to plot 2h and f of 2h, you can see it decays to exactly 25 now, because it's losing half every time. If we were to do 3h and f of 3h, it would decay 1/2 one more time, right? Now sometimes it can be interesting to write this in terms of using E, because how fast is the substance decaying? I'm kind of torn. You know what? I'm not going to do that in the lesson. I may do that in the discussion area. I'm just going to make a note to myself. How do you use E to do a discussion, to do one of these? So it'd be kind of interesting. Is that I'm going to ask you. I'm going to pose this question to you, and if no one answers it, I will. Can you rewrite this equation, P of t equals 100, 1.2 to the negative t, in the form P of t equals 100 e to the kx? Okay, so can you figure out how you would write it using e instead of 1.2? Okay, actually a really good question. That it will help you, I think, on the thinking or communication section. Can you convert it? Okay, so give that a try, or look in the discussion area and see if you can find it. But anyway, that's there for you. Now, question B says, how fast is the substance decaying at the point where the half-life is reached? So let's go back and answer B. How fast is the substance decaying? Is equal to, what we want to know here is P prime of whatever we said. So negative ln 0.5 over ln 1.2. Right? So all we need to do is sub that number into P prime, and that will give us the answer. So let's go back and write the P prime. So P prime t is equal to, okay, so 100. Remember, 100 is a constant, so it just kind of sticks there. And then we do the derivative of the exponent. So 1.2 to the power of negative t, don't touch it, multiply by the correction factor, okay, and then multiply by the derivative of the exponent. So that would be everything you see. So all we do here is we're going to put in p prime of, what was the number again? 3.8018. And then we just plug it in. So 100, 1.2 to the power of negative 3.8018 times ln of 1.2 times negative 1. Oops. Okay, and if you do that, let's just go back here and get it. So I'm just going to type derivative f. So you can see it changed 1.2 to 6 over 5, but it did give us the same answer. It's a 100, it's a negative 100, it has a ln 1.2, and then it has 6 over 5, or 1.2 to the power of x. Now if we do slope tangent AF, the answer we're expecting is negative 9.1616. If you plug our number into the derivative, you get negative 9.1161. So we get p prime of 3.8018 is equal to negative 9.1161. And now, so what of course, it's a rate of change, so we want to write the answer in the proper format. So the substance is decaying at a rate of negative 9.1161. Let's go back and read what it actually was. It says the percent of material left after t years. So I say negative 9% per year. Okay, the substance is decaying at a rate of negative 9.1161% per year, and that is my final answer. Okay, so there's some text work for you to try. However, I want to also do with you, I want to just do, while I've got you here again, if you're not interested in this, then you can just pause and finish it. But let's do an example question from the assignment. This is, I think this is just fascinating. I really, if you go back to what we learned about the demand function last unit, right? In our study of economics, we said the demand function was like a linear function that always decreased. And the idea was, right, I guess an x would help. Okay, the idea behind the demand function was you could plug in the number of sales you wanted to get, and it would spit the price back at you. So for example, if I want to sell 1,000 objects, it tells me I need to charge $40. If I want to sell 2,000 objects, I can't. Basically, I'd have to give them away to sell 2,000, right? So this was the idea behind last unit. And the revenue function, we said, was x times the demand function. And this produced a quadratic where you could find, what price would be the ideal price to set in order to get the correct number of sales in order to sell the most material. Now this was all based on the assumption that if you raise the price, so let's just find what I was doing. Last unit we used a linear demand function, and it was based on the assumption that raising the price by a set amount would reduce customers by a set amount. But of course, this assumption is really not the best in terms of, real life applicability, because probably more likely, if you raise the price by a certain amount, you are going to reduce the customers by a percentage. So for example, if I raise my price, by $1 or $5 or whatever, it might be more realistic to say I'm going to lose a certain percentage of my customers as opposed to, just losing the same amount all the time. So here, this question, it hypothesizes a new type of demand function where the demand function is given to you here. Okay, so P of x is equal to PO times e to the power of negative kx. It tells you k and it tells you PO. So let's just type this into GeoGebra, and I want to show you how this is a bit different from the idea that we just talked about in the past. So let me change my demand function a little bit, And let's say instead it was plus 9 because, and let's say it's 1 over 250 instead. Just give this a little bit more. Okay, anyway, so here's the linear demand function, right? Now let me graph the new demand function that they said. So they said k was 0.001. Let's get more decimals here. Okay, so that was k. Then they said PO was 9. And then they said the demand function, which I'm going to rename. Yeah, let's rename it. Oh, sorry, silly animation thing. Let's just rename this demand function to the linear demand function, okay? And then we'll call this new one the new demand function. So it's PO e to the power of negative kx. Okay, and there you go. And I'm just going to quickly change PO back to 9. Now, look at this as a demand function, the brown one, right? Like our original one, it has a price that is too high, and that is represented by P of 0. It in fact is represented by the coefficient at the beginning of the equation. This would represent if you charge this much, you are going to have no customers. No one is willing to pay that. However, instead of the odd assumption on the other side, where you would eventually get, you would charge $0, which makes no sense. The exponential has a better feature here, right? Where it has a horizontal asymptote, where you could always get more sales. You could get P of 4,000, P of 10,000, lowercase p, and so on. It's just, instead of it ever becoming a negative number, like you'd have to pay people to ride the bus, it continuously returns a number to us. It's just a smaller and smaller value. Right, so it's like, how much would you have to charge in order to get 4,000 people to ride this bus every day? You'd have to only charge 16 cents, right? Now compare that with what the linear function would predict, right? The linear function predicts that to get 4,000 people to ride the bus, you have to give them $7. I mean, it just as an assumption, it just doesn't make a lot of sense. So a communication question I could see asking you, which would be something like, so communication. What is the advantage of using an exponential function for a demand function, P of x, in in economic optimization question? And your answer could be something like, it has a more realistic relationship where your price has to drop a certain percentage in order to get more people to come. So for example, look at P of 1,000 and then look at P of 2,000. And then what we can do here is we can compare that with P of 0. So if I go P of 0 divided by P of 1,000, I get E. And if I get G here, which is P of 1,000 divided by P of 2,000, I also get E. So the idea is, instead of like raising my price by 50 cents to get 100 new customers, it's every time I want to gain customers, I have to take off a percent of the price instead of a fixed amount, right? So here, to gain X customers, I have to reduce the price by Y percent instead of Y amount. And this often is a more realistic kind of view. Now again, because this is a decreasing function, and this function tells you the price to charge, the revenue function is actually still the same. It's x times P of x, right? It's just now, instead of it being a quadratic, it is an exponential. And you can see that just like it did in the past, it has an optimum number where I should get a certain number of customers at a certain price in order to do the best I can do. It's just instead of being a parabola where one side of it really makes no sense, it becomes negative, you can see that the kind of quote parabola tails off into a horizontal asymptote. Now obviously again, it's not in this company's interest to get 6,000 people riding the bus because they'd have to charge so little that they're not making a lot of money. But the same idea, the same principle is here. There is going to be a maximum, an ideal value. Let's try and solve this one and then we'll come back to the picture. Okay, so again, it tells you what the demand function is. It tells you what the demand function means, it reminds you. And then it says the revenue function is such and such. Find the price of bus fare that maximizes revenue. So let's draw this out. So we're going to say first that the demand function is equal to 9 times e to the power of negative 0.001x, right? That was our demand function. Our revenue function, therefore, is simply x times that, just like it was last unit, right? Same thing as it was last unit. You just multiply by x, because x is the number of sales and p of x is the price you're charging, right? So now you go, what's the derivative of the revenue? Well, this is a what do you call it? A product rule. So g prime h plus h prime g. And let's quickly write out what all of those are. G of x is, let's say, 9x. Actually, no, sorry. Let's just make g of x just regular x. Therefore, g prime is 1. Okay, easy enough. Now the other function, which is actually our demand function, so I could have called it p, I suppose, but anyway, whatever. H of x is 9e to the negative 0.001x, and therefore h prime is equal to, okay, so let's again copy it out, 9e to the negative 0.001x, multiply by the correction factor. We're working with e, so we don't need a correction factor, and then multiply by the derivative of the exponent. We get 0.001. Okay, so we could make this a little simpler on ourselves if we say h prime is equal to negative 0.009 e to the power of negative 0.001x. Okay, so let's do the product rule now. The derivative of the revenue is equal to g prime, which is a 1, times h, which is 9 e to the negative 0.001x. Okay, and then plus, now we do h prime, negative, so let's change it to minus since it's negative, 0.009 e to the power of negative 0.001x. Okay, and then we multiply all of that by g of x, which is again simply x. Now again, look at what you see here, and obviously the 1 I can just ditch. I don't need a 1. Well, I'll leave it there, but it's just for this step. But let's write it again. Okay, let's ditch the 1 because it's not needed. Now I notice that this e and this e are common to both sides. Okay, therefore they can be factored. Let's just okay, so let's factor it to the front. So what will be left when we're done would be a 9 minus something. Okay, so let's bring this common factor to the front. Okay, what would be left of the left side is just a 9. What will be left of the other side is 0.009x. Okay, now when is the revenue function equal to 0? The revenue function is equal to 0, or excuse me, the derivative of the revenue function is equal to 0. Well, we know that e to the power of negative 0.x is never equal to 0, so that can't give us a solution. So the only place we can look for a solution is the other bracket. Okay, so 9 minus 0.009x equals 0 would be the solution that we're looking for. So 9 equals 0.009x, which means 9 divided by 0.009 equals x, which means 1000 equals x. Okay, and so that is our max, our critical point for this function. Now again, as usual, this time actually it is an open domain this time. So let's just write that down. So it's an open domain, right? X is greater than or equal to 0, because you can't sell a negative number of objects. But unlike the linear ones we worked with last unit, there is no upper limit to this. So 0 is the lowest you can have, but there is no upper limit. So how do you solve it when it's an open domain? To solve an open domain, you must check the critical point, and then if there's only one, right? Okay, and sorry, let's clear this one. If there is only one critical point. Okay, to solve an open domain, if there's only one critical point, prove it is a max. If there's more than one critical point, you have to graph it. So keep that in mind. Anyway, in our case, there's only one critical point. So we just need to prove, we need to prove that P of 1000 is a maximum. If we can prove that it's a max, since it's the only critical point on the domain, it must be the absolute max. Okay? So since P of 1000 is the only critical point, it must be an absolute max if it is a local max. Okay? So let's prove that it is the local max. So to do that, what we're going to do is let's do the second derivative test here, since we haven't done this in a while. So P double prime of x. Sorry, not P. Sorry, it's not P. I'm thinking of the other question. It's R. Sorry, make some corrections here. Okay, so our derivative, let's go back to our derivative here, was this. Okay, so let's just write this down again. R prime x is that. Okay, so the second derivative, right? It's a product rule where we have two functions. So we have hg, g prime, plus g, h prime. Okay, our four parts are e to the negative 0.001x. Sorry, so let's call that one h. Our g function is 9 minus 0.009x. Our derivative of h is e to the negative 0.001x times negative 0.001. Okay, our derivative for g is simply negative 0.009. Okay. So we have the four parts we need. Let's make the derivative now. So I start with h. Okay. Then I do g prime. And then I add g. And then I do h prime. Okay, so all of that. So this is r double prime is that. Okay, so to finish this off, I just need to sub in r double prime of 1000 and see what I get. Okay, so just to make this a little bit simpler, let's find out what e to the negative 0.001 x is. And we're just going to do q of 1000. And it's 0.3679. So this part, 0.3679 times negative 0.009 plus, okay, so we have 9 minus 9 minus 9, so I think that should just give us 0. So the second bracket you can see is just equal to 0, so we get r double prime is equal to, and then we just going to multiply this L, negative 0.009, negative 0.0033. Okay, since the only critical point in the function is on a concave down interval, it is a local max. Since it is a local max and an absolute max. Okay, just going to very quickly double check that work here. So let's do the derivative of r, and then we go the root r prime is 1000, very good. And then we go the derivative of r prime is this thing. So that's the derivative we just got. And r double prime of 1000 is negative 0.0033, like we said. So we've proven that it's concave down at that point, and it's the only critical point. Therefore, it must be an absolute max. Now, be careful with this question. I've done a lot of work, but I haven't actually answered it. It says find the price that maximizes revenue. The price that maximizes revenue is equal to lowercase p of 1000. Remember, x equals 1000 is the number of riders, but it doesn't say the price we should charge them. The price we should charge them is according to the original function, e to the power of negative 0.001 times 1000. Okay, so that's what we just need to plug into that and get the answer. So you find out that p of 1000 is equal to 9 times e to the negative 1, and p of 1000 equals 9 over e. And that's what we should charge. So let's do 9 divided by e. And we get $3.31. Okay, now let's go back to my question. So I'm going to put in $3.31. Submit. And I'm good. Okay, so again, obviously the amount of work I did is not the amount of work you need to do for the assignment, but you might want to do it on the just on the test, right? You got to make sure you know the steps, and you can go through the like proving it's a max and all that stuff. Okay. Anyway, questions, please post to the discussion area, and again, I'd like someone to try to tackle that one.